Hello everyone, I am Dr. Kashif Iqbal from University of Wa from Department of Chemical Engineering. Today we will learn about pinch technology and we will learn that how pinch technology is important in the chemical process industries and how technology make the energy recovery for the plant and increase the energy efficiency and energy uh, revenue from the plant. So what is pinch? Pinch analysis is a methodology for minimizing energy consumption of chemical processes and plant by calculating the thermodynamic feasible energy targets. Targets means then we need to minimize the energy consumption within the plant and achieving them by optimizing energy recovery systems, energy supply methods, and process operating conditions. There are many names which can be alternatively used for the pinch technology or pinch analysis. We can call it as a process integration, heat integration, energy integration, and pinch technology. In all these terms, we can say that our prime purpose is to maximize the process to process heat recovery and reducing the external utilities. So what we do in the pinch analysis? In the pinch analysis, we firstly analyze our process plant. We analyze our plant that in which site of the plant the heat is the surplus, which units are producing most heat and energy, and whether this energy is going to waste or going to exit into the environment, or whether we can use it energy in the other processes. So after analyzing the total process regarding their heat flows, we establish energy targets that how much energy we can reduce from the plant side. This is very important because if we set our targets, then we can identify the inefficiencies within the plant. So thirdly, when we set the targets, then we identify the inefficiencies based on the target that we introduce in our section 2. And then finally, when we identify the inefficiencies, and then on those efficiencies, we define the process improvements. And these inefficiencies could be the bad insulation in the system, the energy leakage, and many other things like this. So this is a very simple example from the real plant in which a reactor and a column is attached, and the total heating utility of this small process is 1720 kilowatt, and the cool utility for this whole system is 654 kilowatt. And total of 6 units are employed in which the heat is being transferred from one stream to another stream. We can see that there are 3 stream to stream heat exchangers, 1, 2, and 3, and 3 other exchangers are being applied in this system. So when we apply the pinch in this system, and we can see that the number of utility units is reduced. There are utility systems 1, 2, and 3, and these 3 utility systems are reduced to only 1 utility system, and the process to process heat recovery is being increased with the help of pinch technology. And we can see that the total cooling utility demand is 0 here, and the heating utility is also reduced from 722 kilowatt to 1068 kilowatt. You can also see that the number of units that were used here for the heat transfer from one process to another process or one stream to another stream was 6, and the total number of units after pinch analysis is reduced to 4. So this analysis is very important because not only we decrease the number of units, which will have a very direct impact on the capital cost, but also the operational cost, because the operational cost for the 6 units is much higher as compared to the operational cost for 6 units. So in the key concept of the pinch analysis, basically we set the targets that how much energy we want to reduce, and then we work on it. The energy reduction is a very promising topic in the previous years, and almost 10% energy consumption per year is demanded. Just like the other entities like the productivity targets in the industry and management, this is a very arbitrary figure. It could be changed from one plant to another plant, but the 10% reduction may be a very good target for a badly planned design and operated plant. However, on a good plant where continuous improvement has been taken place over the year, a further 10% may be possible. So here is the example of 4 stream where 2 are the cold streams, stream number 1 and stream number 3, and stream number 4 and stream number 2 are the hot streams. These are their initial temperatures, their final temperatures, and the heat capacity flow rates. And these are the heat duties of each stream, which can be transferred from one stream to another stream. For example, the cold stream have total 230 kilowatt, which can be taken from the other hot stream. Just like this hot stream, it has the 330 kilowatt, which can be given to other stream. So these streams can be used from one unit to another unit, so that the utility requirement from the utility section are reduced. So for the pinch technology, there are 2 very famous methods which can be used for the problem solution. First is the problem table method, which can be used for small scale problem. It is very easy and handy when the system is little and we have a very few streams. It will give us a very quick answer. It will give a very quick answer in a very short time, that how much would be the hot utility, how much would be the cold utility, and what is the hot pinch and the cold pinch temperature. Second one is the graphical techniques, and there are other mathematical approaches in which we use the algorithm development, and we solve the whole problem, complex problem, with the help of some computer solver, and they are very accurate and very time efficient. So when we talk about the application of the pinch technology, nowadays they have defined for the process synthesis and the optimization of the current plant, which we can say that we can retrofit the plant that are being exist. In the process synthesis, we can make the flow sheet, we can size our equipments, and after sizing the equipment, we define that how much energy can be recovered in the newly designed process. But in the retrofit approach, we basically optimize the process that are already defined, and in the defined moment, we didn't optimize that process for the energy recovery. So this is the example in which a reactor, in which reaction is taking place. The feed is coming in from 20 degrees centigrade, and after heating the feed, it achieves the temperature of 200 degrees centigrade and get into the reactor. And after the reactor, it comes out with a temperature of 150 degrees centigrade, and product is cooled down to 50 degrees centigrade. So here is the opportunity that we can transfer the heat within the system. as we can say that in the current state, the system taking the heat from the utility section and giving the heat to the utility section. But there is the opportunity that one stream uh, want the heat and one stream can give the stream. So we can exchange heat between these two streams, and the utility requirement for the whole system can be reduced. So it is good to explain that what is the stream in this case. Every feed, every stream which can uh, heat up would be a cold stream, just like this one. This is a feed stream where initial temperature is lower and final temperature is higher. So this could be a cold stream, and the steam where the initial temperature is higher and final temperature is lower, it could be the uh, hot stream. So a stream is an entity where the composition of the material before and after the exchange of heat is not vary. So someone can say that the reactor could be a stream. No, it cannot be a stream because uh, the composition of the point where the feed getting in and the composition of the product that is going out from the system is not same. So we cannot define a reactor as a stream. So these two streams have this data. The cold stream have the mass flow rate, this one, the specific heat flow rate, the initial and final temperature, and their heat loads. So we can make such assembly to transfer the heat. We can put a heat exchanger here, and we can transfer all the heat from cold stream to hot stream, or hot stream to cold stream. So this is the main composite curve where we use the temperature enthalpy diagrams to draw the curves. To draw the curves, it is very important that there must be a delta T between the hot and the cold stream. The solid line is the cold stream and the dashed line is the hot stream. This is the delta T between the hot and cold stream. For that system, that is the heat duty, and this is the cooling duty for the system. And this is the region where hot and the cold stream will exchange heat. So in the enthalpy temperature diagram, we need a graph where we draw the lines according to their temperature. For example, the hot steam was from this temperature to 180 degrees centigrade, from 50 to 180 degrees centigrade, and the cold steam would be from 20 to 180 degrees centigrade. But we can see here that the hot steam and the cold steam are crossing each other, which is basically a violation of the basic laws of the thermodynamics. So we need to change or shift the cold steam so that there must be a temperature difference between both the streams. So how we will do it? We will do with the help of shifting the cold stream downward like this. We will shift the stream so that the temperature would not change. The temperature of this stream before and after is the same, but the total load of this stream shift from here to here. So in shifting the curves on the axis, we can say that the total duty of the steam would be same, the temperature would be same, but we just only shifting the steam from one place to another place so that we can show a temperature difference between the streams. So we can conclude the two things from the composite curve, that as we increase the delta T between the hot and cool streams, the hot and the cold utility will be increased. And secondly, we can say that as much as the hot utility would be increased, the cold utility would be decreased, or they can exchange as one and the second utility would be changed. So that was the example of two-stream system. If we have the more streams, then we can calculate their CPs like this. For example, in this temperature range, there is only one curve. In this temperature range, we have the three curves. So the enthalpy of these three uh, composite curve would be added up like this. And finally, we'll get the composite curve like this. So finally, the pinch analysis have the two streams, hot and the cold stream, and this is the pinch point. Above the pinch, this is the region where can the heat transfer, and the below the pinch where the heat can be transferred. And this is the heating utility for the whole system, and this is the cold utility for the whole system. So when we define the pinch point and the above and the below pinch regions and hot utility and cold utility, on this basis, we will draw a heat exchanger network in which we exchange heat between the streams. We will check all these things in the next lecture, where we will define the problem table method first, and then we will make this heat exchanger network. So this is all for today. Thank you.